Concept pros and cons. On the pro side, you've got flexibility in the geographic location, the launch location, that performance boost I was just talking about. You have flexibility in the launch azimuth and the orbit inclination, essentially by moving around the launch point. Also, the ability to move that launch location for safety benefit. When you launch something to orbit, you've got hardware falling out of the sky. The first stage and second stage don't make it to orbit, and they're too big to burn up in the atmosphere when they come back. So what happens is that you have to clear the shipping lanes, you have to coordinate, make sure that the boats aren't out there. It's expensive to do that. A lot of launches get delayed because there's a boat and they run the risk calculation and it's too high, so they either have to get them out of there, and then there's a delay and they miss their launch window. If you could simply move over 10 miles and re-enter the coordinates for the launch on the fly, you can avoid most of that. Also, weather avoidance. You get a series of thunderstorms coming through. I'm sure you're used to hearing about weather delays and landing the shuttle at the Cape, et cetera, et cetera. If they could have up and moved the runway 40 miles laterally or landed at Orlando, they could have avoided a lot of that, but you can't on a landing. But you can on a launch if it's an air launch. You have a lot of flexibility moving around. I think I mentioned this earlier, the ability to safely, quote, pickle the load. I think that's a bomber phrase from World War II. Probably have to do with the B-29s hitting the pickle barrel. Anywhere in the flight profile in case of an IFE, in-flight emergency. Also the ability to carry a wide variety of different launch vehicles. The launch pads are set up for a rocket, or this rocket, or that rocket. With this, it's fairly easy with adapters to be able to handle a bunch of different geometries of launch vehicles. The other thing is it gives you a pretty safe explosive blast proximity distance for the aircrew if you go remotely piloted on the glider. If it's a solid, that's not that much of an issue. If it's a cryo, it becomes more of an issue. If it's a hypergolic, it is an issue. And so having the aircrew be a couple thousand feet out in front of this with maybe 400 knots of air blowing in the other direction as they're flying along tends to make it a lot safer. And the ability to efficiently lift the large booster to altitude and so forth, take the launch range assets with you to the launch point, results in a cost-effective platform with low recurring maintenance because the airplane is so simple. And again, open up the launch windows, more opportunities for flying and putting things to orbit. Again, nothing's for free. On the negative side, you've got to increase overhead in doing the launch operation versus a crewed carrier launch aircraft. You've got two airplanes that you're flying. It's a little bit more complicated in that it is tow. So there's more things that can go wrong, and you have to be able to manage and mitigate the risks for that. It does require the design and fabrication of a dedicated launch glider aircraft. On the other hand, so does building a dedicated carrier aircraft. So that's probably a push. Landing after an aborted launch or a hung store, which is where you go to do a launch but it didn't release, may be an issue. Essentially, this is what I was talking about, is you need to be able to land it in the case of a misfire or an aborted launch. The launch operation is a little bit more complicated than doing it from a carrier aircraft from a ground with a crew. And it's more difficult to support the cryo propulsion systems, LOX top-off tank scenarios. There was one launch off the B-52, I believe, where they used the cryo top tank on the B-52. That was the Pete Knight flight to Mach 6.71. They used it once. They didn't use it again. It scared the heck out of them. It's not something that you tend to want to do, is carry around 300 gallons of liquid oxygen in the bomb bay of the airplane that you're flying around. It was also done on one of the X-1 launches off of the B-29, and I believe on that flight they actually had an in-flight fire and dropped the X-1 early. And it basically ditched the propellant and glided to a landing on the lake bed. You'd really rather not do that. It's a little more difficult if you choose to do it. I don't think people are going to be doing that anyway. The technical approach that we're going to take on try to validating the concept, there's 3 distinct flight phases, and I'll touch on it now. Phase 1 is the model test that you see on display. That is basically tow to altitude and instrumented, subscale, remotely piloted twin fuse glider with the representative faux rocket attached. We're trying to assess the feasibility and the viability of the concept and characterize the aerodynamic performance of the mated pair. We're trying to get an early look on whether this is a crazy idea or it might work. It's that simple. Phase 2 is to take the success from that and take 2 full-scale commercially available sailplanes that will look just like that, modify them into a twin fuselage, optionally piloted configuration, towed to 40,000 feet behind either Proteus or White Knight 2. primary goal is a risk mitigation development vehicle, a quick, low-cost way to explore the full-scale operations and identify some of the unanticipated risk areas. There's always something you will learn that you didn't anticipate, and generally it's not something nice. There's not many things you find that are to your benefit. It's something you didn't think about. The capability of that, when we'd be done, is the ability to launch a 5,000 or 6,000 pound rocket placing about 100 pounds into orbit. This is an 81-foot wingspan sailplane with a 20-foot center section custom, but the rest of the glider, other than beefing up the landing gear, would be pretty much stock. Our idea is to put leave the pilot with the cable and push rods hooked up to the left side of the fuselage, put a digital flight computer in the right side, and put what we call CPTs. It's a control position transducer. It's essentially a potentiometer like you have the sticks on the transmitter, but it's got a spring on it that loads it to one side, and then you put a pulley on a reel, and you hook that to the control surface. And as you move the surface, the pot turns, and with that, you tie that into your data system. You can tell where the surfaces are at any point during the flight. That's how you analyze the aerodynamic performance of the vehicle. So what we would do is we would have that hooked up to the stick and rudder on the airplane with simple pass-through gains, such that when the pilot moves the stick, the push rods on the left side, the left fuselage, you get 12 degrees of up elevator. You get 12 degrees of up elevator through the computer through fiber optic to a servo actuator. So the right-hand side of the airplane would be fly-by-wire. And the way you handle not having to have Class A software, which means human-rated software, which means you test the wazoo out of it, is you show through analysis that if you pull the circuit breaker on the computer, if the computer does an upset on you and you can't reset it in flight, you pull the breaker, pick servos when you design it that just float, and we think we can show through simulation analysis that you can fly the airplane back home safely with just the left side. There's lots of people here who have had linkages break, servos fail, things quit. As long as the surface doesn't go hard over on the aileron on one side, generally you can land the airplane. Same exact concept. Simple. The reason for doing the fly-by-wire is you can't take a piloted airplane that's unpressurized above 25,000 feet for any length of time. So the idea is to develop all the software algorithms while you're doing this, have the computer run those algorithms as if it was remotely piloted, capture the data, throw the data in a bit bucket, analyze it after the flight. Once you think you've got it sorted out and you actually know what you're doing, then you take the airplane down for a few months, convert the rest of the airplane to fly-by-wire, remotely piloted, and now start towing to 40,000, 50,000 feet behind Proteus and start launching rockets and demo the concept further. Phase 3 is to take the risk mitigation from that, because by the time you've done this, you pretty well have figured out what's going to go wrong. You're into it about 1.5 years, 2 years, almost 3 years of flying these things. And most of the things, Murphy's Law, what can go wrong will. Okay. He was a captain at Edwards Air Force Base, for those who didn't know that. It's a true story, back in the 40s. And so the idea is to take everything that you've learned and apply that now to an X-plane. It'd be a purpose-built, not a modified, but a purpose-built from scratch aircraft on the order of 35 to 40,000 pounds, remotely piloted, capable of carrying an 80,000 payload to altitude and air launching it. That would put about 1,600 pounds to orbit. Rule of thumb, if you air launch something from about 40,000 feet with a solid rocket, about 2% of the rocket's weight is the payload that you can put into orbit. So whatever it weighs, about 2% is a good rule of thumb. We just had, we commissioned 3 independent studies of this concept. We've done our own analysis, but we commissioned 3 independent studies with some notable names. Alan Wilhite is a professor at Georgia Tech. He led the systems analysis group at NASA Langley for 20 some odd years, did an independent assessment of this, which he finished up about 6 weeks ago. Last Wednesday, Burt Rutan, who was funded through a subcontractor of ours, did a 100-day study on the concept and gave us a 5-hour outbrief of his results of the concept, and it was very favorable. The numbers that he's showing, not reviewed, need to be scrubbed. Granted, he's a great designer, probably the best one ever. Everybody's fallible, makes mistakes, so we need to review the data, but the numbers he's showing is between a 24 and a 40% performance boost by doing the air launch with some fairly novel techniques. And there's a DARPA study that's being used for another program that's suggesting as much as a 25 to 40% cost savings or reduction in pounds to orbit with air launch. And that was without the performance boost that Burt was talking about. And then the third study is, you guys remember Helios, AeroVironment out in Simi Valley, did the 100,000 foot solar powered airplane, 300 foot wingspan. had Airtronic servos on it and big electric motors. I think they made their own brushless motors. Ray Morgan was the vice president of the Aero Group that developed all of that, and he's doing an independent analysis, and that'll be done in about 2 weeks. The idea is if you've got 3 studies that give you essentially the same results, and with those kind of resumes behind it, nobody's going to argue with whether or not it's feasible. Then it really boils down to, okay, what kind of money does it save you? How cheap could it be?